This video lecture is meant to cover the information found in Unit 12, Calorimetry and Phase Changes. And in this video lecture, the focus will be on heating curves and phase changes, and we'll cover the objectives numbers 1, 5, 6, 7, and 8, interpreting heating curves and learning about different phase changes and what happens with energy transfer in those phase changes. I'm going to start off by looking at this video that will give you an animation to try to help you see what's going on with the molecules when we have a solid, a liquid, and a gas.
The states of matter are gas, liquid, and solid. Gases assume the shape and volume of their container. Particles of a gas are separated from each other, move in straight lines, and in a completely random manner. They change direction only when they collide with each other or the container. Liquids have a definite volume and assume the shape of their containers. The particles of a liquid are closely spaced, and so their motion is still random but much more limited. The particles slip past and collide with near neighbors. Solids have a definite shape and volume. Particles of solids are in fixed positions and collide only with near neighbors.
All right, so what we see here is we have these different phases of matter, solid, liquid, and gas, but what happens during a phase change? All right, so during a phase change, you have 4 graphics on this particular slide. What I'm going to show you is an animation trying to attempt to show you what's happening with the molecules as the solid is turning into a liquid and a liquid is turning into the gas. So here we have the starting point of this simulation. What we have is a block of ice, and so what you can see with each one of these dots here in the middle of this beaker, those represent an assortment of molecules of water that are stuck, frozen in that ice cube. We are heating it at a constant rate of heating, and we're going to watch this thermometer as we start this simulation. So what we see here is as this ice is heating up, right, so we had ice starting at a temperature below 0, and as we heated it, the temperature rose on the thermometer. Now watch what happens as the temperature reaches 0 degrees Celsius. We start to see the molecules of the ice cube get loosened up and turning into a liquid. Notice that while the ice is melting, the temperature is staying constant at 0 degrees Celsius. Once the water has been all melted into liquid, the temperature can then start rising. And so the temperature will start rising, the molecules will move faster and faster, the kinetic energy is increasing. And at some point, certain molecules will have enough kinetic energy to actually escape out of the liquid and turn into a gas. And you'll see here that as the temperature approaches 100 degrees, that's when those molecules have enough kinetic energy to escape and boil away. Notice while the boiling is happening, the temperature is remaining constant at 100 degrees Celsius. All the energy that is being absorbed by the liquid water is being used to accelerate the molecules out of the liquid phase and into the gas phase. Once all the molecules are turned into a gas phase, the temperature can again rise. So you saw this when we did the snow melting lab, and but here this is sort of the molecular explanation of why you saw what you saw. So you have this graphic on your handout, and so what we have here is we had ice, and it was heating up. That was less than 0 degrees Celsius, and it hadn't melted yet. So this is just solid ice heating up, and it was all at a temperature lower than 0 degrees Celsius. All right. At 0 degrees Celsius, this is what we call the melting point for water, and what you can see here is that this cube, this was the original cube back here, this cube started melting, and so these liquid molecules were able to turn into a liquid, and they had more motion at that point in time. The temperature stays constant at the 0 degrees Celsius while the melting is happening. Once the ice had turned completely into liquid, you have these molecules down here that have more motion, and at this point the temperature could then rise. So between 0 and 100 degrees Celsius you have a liquid that is heating up, but there's no phase change at this point in time. So here you have the liquid, here you have the solid, but while the solid turns into the liquid you had the temperature staying constant. Once the temperature hits 100 degrees, that's the boiling point for water, and it's this phase where liquid could turn into a gas. And so there's a phase change right there. And while the change was happening, the temperatures remained constant at 100 degrees Celsius. All right, please find in your handout, you'll probably have to flip some pages, but you will find a handout that has this graph on a full page of the paper, or at least a half page of the paper, and I would like us to label it. So this right here resembles the heating curve that you constructed for the snow. This range of temperatures is a little bit wider than what we saw before, but there's a graphic right here showing you that we're starting with a solid. So this is the solid starting at time 0. And so while water, and so here we have solid that is turning into a liquid, which will ultimately turn into a gas, right? And so this graphic right here, we have solid turning into a liquid. Here we have a liquid turning into a gas, and trying to show you molecularly what's happening. So this is what we call a heating curve. You can see over a range of times and temperatures that the temperature is definitely rising over time. So this represents the heating curve of water, and I'll explain how you'll know it's water in a second. But because the overall trend is that there's an increase in energy, increase in temperature, this is what we call an endothermic graph, because endo means in, therm means heat, so energy is absorbed by the system, and in this case the water. Okay, and we see that because the overall trend of the graph is going up. So if we have points A and B, so points A, B represent the solid phase, and so what we have here, this is solid, and in that phase the solid is warming up. From points B to C, we have a solid turning into a liquid. That is happening at a constant temperature, which is 0 degrees Celsius. So this is what we call the melting point. And this is one of the ways that we can identify this substance as water, is that the melting point is at 0 degrees Celsius, and that is unique to water. From point C to point D, here we have a liquid that is heating up. And from point D to E, we have the liquid turning into the gas. And then from point E to point F, we have a gas that is heating up. All right, so again, you saw this on your snow, when we heated up the snow. You saw this from point B to point E. We were not able to take the temperatures of the solid snow any colder than 0 degrees because it was a pretty warm day outside. All right, the other way you can identify this as water is if you read over while this was happening right here, and of course this is called boiling. While the water was boiling, the temperature remained constant at 100 degrees Celsius. So that's what we call the boiling point, and those are identifying features for water. Okay, so this is a heating curve for water. All right, you'll find another graph with the cooling curve for water. Again, we can recognize this as water because the first plateau is at 100 and the second plateau is at 0. So this tells us that this is water, but it's not heating, this is cooling. So this is a cooling curve for water. And in this case, because the temperature is cooling down, this is said to be an exothermic process. Heat is exiting the water, and consequently the water is cooling down. All right, so what we have here from point A to point B, it's the reverse of what we saw with the heating curve. So what we have here is we have a gas that is cooling. And as soon as that gas hits 100 degrees Celsius, that gas will turn into a liquid. This is a process known as condensation. And so this point right here is known as the condensation point. So that we would call that A to B. Points B to C is where, well, A to B was the gas cooling, B to C is the condensation point. From C to D, this is where we have a liquid that is cooling. From D to E, now we have a liquid turning into a solid. Notice that at this point, if we read this over on this graph, it hits that 0 degree mark. This is not that we wouldn't, it's the same temperature as the melting point, but since it's not melting, we can instead call it the freezing point, because now the liquid is freezing into a solid. From point E to point F, what we have here is we have a solid that is cooling down. And yeah, I think that represents all the phase changes that we need to recognize here. Okay, so heating curves, the general trend is up and to the right. Cooling curves, the trend is down and to the right. All right, so phase changes. We're going to take a closer look at those phase changes. Exothermic. As you recall, exothermic is basically cooling with two plateaus. Okay, they're going to have two plateaus and three. Oh, I'm not doing a very good job drawing that line. Okay, so you're going to have two plateaus. The first plateau represents condensation, right here, and the second plateau is freezing. So that's an exothermic phase change. Endothermic phase changes. Your overall trend of your graph is up and to the right with two plateaus as well. The first plateau is melting, and the second plateau is boiling. So the flat parts of these heating curves are where there are phase changes. And you can ultimately, if you read back to the melting point and the boiling point, those numbers can be used to identify the substance. On the exothermic, we have the condensation point and the freezing point, which we discovered the freezing point is equivalent to the melting point of a substance, and the condensation point is equivalent to the boiling point. The only difference is which direction the heat is going in that particular phase change. All right, so let's take a closer look at these endothermic and exothermic phase changes. We're back in your handout. All right, so endothermic phase changes, we'll look at the first one. Melting has a fancy name in chemistry. It's called fusion. So it's often referred to as the heat of fusion, how much energy it takes to melt a substance. So since this is melting, for example, water, if you start with water in the solid phase, of course that's ice. And you turn it into water in the liquid phase. Of course, that's just regular water. You have to add energy to that. And I'm going to tell you that specifically, there's a very specific amount of energy that is required to take 1 mole of water and convert it into 1 mole of ice and turn it into 1 mole of liquid. It takes 1,440 calories of energy to do that. So this number is called the heat of fusion for water, how much energy it takes to melt 1 mole of ice. The melting point for water that this phase change will happen at, of course, is 0 degrees Celsius. We just saw that on the heating curve. Another endothermic phase change is boiling. Okay, boiling, the fancy word for boiling in chemistry is called vaporization. Vaporization is when you have liquid water and you turn it into gaseous water. And if you want to take 1 mole of liquid water and turn it into 1 mole of gaseous water, it is going to take a certain amount of energy, 9,730 calories. So this number is a very specific number for water, and it is referred to as the heat of vaporization of water. Notice that it takes more energy to vaporize a mole of water than it takes to melt 1 mole of water. It's a lot more energy to separate the molecules from liquid into the gas phase than it does to separate the molecules from the solid into the liquid phase. The boiling point for water, of course, is 100 degrees Celsius. That's the temperature at which this phase change will happen. But there's another phase change which was not represented on the heating curve, and that is called sublimation. There's a special process that can happen, and this doesn't happen with all substances, but taking a solid form and directly going not into the liquid but into the gas phase. Right? So solid turning into a gas is called sublimation. There's only a few things that can do this. Ice can do this, but only under lower pressures, like at high altitudes. And in certain situations, sometimes it'll happen where we live, but mostly it happens in high altitudes. Many cities in Colorado will do this, where the ice pack, the snowpack will just disappear and you won't see any evidence of liquid. It just, the solid snow just seems to dissipate and shrink. Solid carbon dioxide can do this. It's called dry ice. If you were to take dry ice and just leave it on the countertop, it just shrinks. It doesn't melt. It just evaporates away. And then iodine can also do this. So not every substance can do this. It does take a fair amount of energy to take 1 mole of solid water and turn it into gaseous water. It takes 11,170 calories to do that. Okay. All right, let's take a look at the exothermic phase changes. Freezing, which is also in more technical terms referred to as solidification, or crystallization. Freezing, of course, is when you are taking a liquid and turning it into a solid. And notice now that this is an exothermic phase change, which means the liquid water is going to lose energy. So now we're going to show energy on the right side of the equation. Now notice the reverse of this, a solid turning into a liquid. It took 1,440 calories to melt that water. So when you freeze that water, you get that same amount of energy back. All right? So that same amount of energy it took to turn a solid into a liquid will now be released, and we'll show that energy on the right side as a product. So exothermic equations, you'll see the heat term on the right side as a product. The freezing point of water is at 0 degrees Celsius. We saw that on the heating curve. The second exothermic phase change that we're going to take a look at is condensation. Okay, condensation is when the gaseous form of a substance turns into the liquid form. This is essentially dew on a summer morning, or when you see your beverage glass getting all sweaty on the outside of it. That's condensation. It's an exothermic process. As the water cools down, it has to release heat. In this case, if you look back to the heat of vaporization, this is the reverse process. So that 9,730 calories you had to put in to make the water boil will now come out as the gas condenses back down to a liquid. Condensation point is at 100 degrees Celsius. Same as the boiling point. All right, well, there's one more exothermic phase change, and that's called deposition. It is the opposite of sublimation. It's when a gas turns directly into a solid, and it has to release heat to do it, and you guessed it, it's going to take 11,170 calories in order for that to happen. All right, so taking what we've learned, I would like you to draw the cooling curve for water. Water's going to start at 130 degrees Celsius, so that's above its boiling point. And we're going to show it cooling down to negative 30 degrees Celsius, so that is below the freezing point. We're going to label the temperatures for condensation point and for freezing point. So at this point, well, on the vertical axis, we know the values for water to be 100 and 0 degrees Celsius. And since the temperature is starting at 130, we can estimate maybe that 130 is perhaps here. And as it cools down and hits 100 degrees Celsius, there will be a plateau, right, while the gas is turning into a liquid. So here we had the gas, here we have the gas turning into the liquid. And then at some point when all the gas has turned into a liquid, the temperature will then go down to when it hits 0 degrees Celsius. And at 0 degrees Celsius, right, so between 100 and 0 degrees Celsius, this is going to be a liquid and it's just cooling down. But when the temperature of the liquid hits 0 for water, it will level off where the liquid turns into a solid. Right? But we need to bring this down all the way down to -30. So once all the liquid has turned into a solid, the temperature will decrease to about -30, which is approximately here. Okay, so this is a solid cooling down right here. So that's a cooling curve of water. The key things here is showing the plateau at the 100 degrees Celsius while it's condensing, and showing the plateau at 0 degrees Celsius where it is freezing. So this is called the condensation point, and this is called the freezing point. Okay, so water has these very convenient numbers of 0 and 100, but not all substances have those same identifying features, right? Nitrogen. Nitrogen has a melting point of -210 degrees Celsius and a boiling point of -196 degrees Celsius. So we're going to draw the heating curve for nitrogen going from -250 degrees to 60 degrees Celsius. We're going to label the temperatures for boiling point and for melting point. Okay, so we're going to start if this point right here is going to be the melting point, and up here this is going to be the boiling point. All right, so the boiling point we said was -196. The melting point is -210. So starting from 250, and this is not to scale at all, so but we can conceptually draw this, that it'll come up to here. So what we have here is a solid, and while the solid is melting at -210, it should be a plateau. Once all the solid has turned into a liquid, the temperature will start rising again. And again, this is not at all to scale. But here we have liquid nitrogen, and then here we have the liquid nitrogen boiling away from a liquid to a gas. We want to bring this up to 60 degrees Celsius, so this graph would have to continue up there to get all the way up to a +60 degrees Celsius. So I'm just going to draw that as an arrow to indicate that it should continue on.